Here we have a contour plot of a function, and I've labeled 2 points. I'm going to give us some direction vectors, and I'd like us to use those direction vectors to determine the sign of the derivative if we moved in that direction. We'll start with the vector direction I plus 2j over the square root of 5. This is a unit vector. You can check its magnitude and find that it's 1. Starting at point P, this is a vector direction that corresponds to moving 2 units up for every 1 unit that we move over. So if we move over 1, we move up 2, and we can draw a vector in that direction. So that's the direction of interest for this directional derivative. Here we are on the line where the function is equal to 1, and if we move in this direction, first of all, we can see immediately that we're moving off the line. And to know the sign of the derivative of the function in the direction of u at the point P, we just need to check, are we moving off the line towards the positive side or towards the negative side? Well, this line is 1, this contour is 0. We're moving towards the negative side, so the function is decreasing as we move in this direction. And what if we head over to Q, and we're again interested in this direction, moving over 1, up 2. Okay, well again we can see that we're moving away from, in this case, the 0 line towards the -1 line, so the function is locally decreasing as we move in that direction. The directional derivative in the direction u at the point Q is less than 0. Now, setting up the same problem analytically, I have the function itself, and then I have the coordinates of the point P, the coordinates of point Q, and the direction in which I'm interested in the derivative. To find the directional derivative of this function at this point in this direction, I'm going to start by taking the 2 partial derivatives, evaluating them at a point of interest, and then I'm going to take their weighted sum with the weights given by the u vector. Taking the partial of f with respect to x, x squared gives us a 2x, negative y squared becomes a 0, and e to the negative stuff up here requires us to use a chain rule. So we still have e to the negative stuff, and then we need to take the derivative of the stuff, and we get this expression. And then if I plug in point P, I plug in a 1 for x and a 1 for y. This term is becoming a 0 up here. X minus 1 is a 0, that's right here, and we get a 2 here, and so we just end up with 2 for this partial. We have an extremely similar expression for the partial of f with respect to y, but now when we take the derivative of x squared, it becomes a 0, and when we take a derivative of negative y squared, we get a negative 2y. Next, we plug in at point P our point of interest, and we're going to get negative 2. Now that we have the 2 partial derivatives at our point of interest, we're ready to take a weighted sum of them to get our directional derivative, and so that's going to be a dot product, and it's the dot product of 2i minus 2j dotted with the directional weights, which are 1 over root 5i plus 2 over root 5j. And taking that product, I have 2 over root 5 minus 4 over root 5, which is equal to the negative 2 over root 5. And this quantity, first of all, we've just actually found how the rate of change of the function in our direction of interest, and it indeed was negative.